Hi everyone, we are from group A17 and the title of our project is Dataset Generation Using Portable Device to Develop Deep Learning Models for Detection of Eye Diseases. So normally for the examination of the eye we use opthalmoscope, which is a huge equipment and only specialists can use this equipment. So in the rural areas we will not be able to find such huge equipment which costs worth of lakhs. So the people over there are not getting examined their eye and are affected by different types of diseases before they are detected, and which will even result in the blindness. So in order to make people in the rural areas also get examined frequently and at the early stage, we are trying to develop a portable device which can be carried anywhere and can be also examined in a non-clinical environment, so that the early examination of the eye of people in the rural areas can help them getting a better vision at an early stage. So the existing system for such type of devices are peak retina, odox and DI. So peak retina is basically a device which helps in checking the sight, and DI is an attachable device for mobile. It is capable of taking the fundus, but the images are just stored but cannot be used for classification. And odox is a device which maintains a constant distance between the lens and the camera, so that we can take a perfect image of the fundus. So all these existing devices has some limitations, like they can only store the videos of fundus, and these are only compatible with Android, not with Android phones. These are only compatible with the Apple phones, which are expensive. So, these drawbacks of all these previous devices led to think of a new model, and this is inspired by the indirect ophthalmoscopy. So, the aim of the portable device is to capture fundus images using Android phones and not using the Apple phones, which will make us the cost less, and which will be also easy for screening of eye diseases.
This is a preliminary experiment which we conducted. This is also known as indirect ophthalmoscope. We used a 20 diopter lens here, and the light source for this is a phone flashlight, and we will capture a video like this, which we captured in a semi-dark room. As we can see, we are getting an optic disc here and the image is blurred. But to deduce and classify any fundus image, we need a complete image of which consists of optic disc and macula. For this, we further need to increase the size of a pupil. So we need to conduct this experiment in a complete dark room. So for this, we need a IR camera to capture the video in a dark room. So this is a Raspberry Pi setup, and this is a Raspberry Pi which we connected to a IR camera so that we can capture the image in dark. And we connected this Raspberry Pi to a screen which displays the image that is captured through Raspberry Pi. And we even connected Raspberry Pi to a laptop where we can view the image of that is captured through camera in a better way. And this is a 20 diopter lens which is held in front of an eye to capture the pupil and the fundus inside an eye. So this is a screen which we already showed, and by holding screen, Raspberry Pi and IR camera in one hand and the lens, this is a 20 diopter lens in other hand, we need to place the 20 diopter lens in front of a eye, and we need to shoot it through the IR camera. So these are the commands which we used, where we created a file name called cookie on desktop, and this is a command to run and record the video. After holding a Raspberry Pi and lens and IR camera as shown before, we made a room dark and captured an eye. So this is a video which we captured through that Raspberry Pi and IR camera. So we can see the pupil size increased as a room is dark, and we captured a video here. But as we can see, we cannot see the fundus that is required, but we can only see the enlarged pupil. So for us to capture the fundus, we need a light, but after focusing a light on the eye, the pupil again reduces its size. So we shifted to next model, ODOX. ODOX equipment, this is a lens holder and this is a phone holder. Here we placed a lens and this is a phone where we placed mobile phone in the lens holder such that the phone flash and the camera is concentrated in the same area. We choose this ODOX because in Raspberry Pi we can only see the size of a pupil increased, but we cannot capture the area of interest, like where we can see both optic disc and macula, and even the same case with an indirect ophthalmoscope. So we used an ODOX because here the distance between the phone lens, phone camera and a lens is constant, so we can get a clear image with an image that is captured with optic disc and macula. Now we need to hold an ODOX in such a manner that the lens is placed in front of an eye. This is a video which we captured using an ODOX. As you can see, we can capture both optic disc and macula in the same frame. So using this image and after further processing, we can classify the image that whether the eye is having a defect or not. We can create an app interface which has a capability of recording a video, capturing an image, and even classifying the image which we give as cat or dog. So here, as we can see in this app, we can even capture an image, and after capturing we have three options whether to save it or retake it and cancel it. So I am cancelling this image, and again here we have an option of recording a video. So even here the same as capturing an image. After capturing a video, we have three options whether to save it to the mobile storage or to retake a video and to cancel it. So here comes a main thing in this app where we can select an image. Like here I am selecting an image of dog, and this says as the image is classified as dog. And next, if we give cat, it says this image is classified as cat. So in this now we can use the same app interface to classify whether a given image as an infected eye or not by just changing the TF-Lite model that can classify the given image as infected eye or not.